So now let's look at what series and parallel resistors are. Because while KVL and KCL, the Kirchhoff's laws, can be used to analyze any circuit, and they are very powerful, and sometimes we are going to have to use that approach. Sometimes simplifying things by doing series and parallel resistances can save us a lot of work. It's going to be a lot easier to do. So, big idea on you can have resistors in series. Resistors in series are two resistors that have the same current. Okay? This is a series resistor. That means they have the same current flowing through them. So if you look at, and if the idea is, if I were to collapse that or replace this circuit with the equivalent circuit, what would it look like? Like, I want to know, how does the potential difference here, they have the same potential difference across the two endpoints, what would the equivalent resistance be? Well, because they share the same current, you know that the voltage drop across R1 plus the voltage drop across R2 is going to equal V. That's like kind of that's like the equivalent of what KVL is, that voltage drop there. Now, the voltage is I times R1 plus I times R2 equals V. You can factor out the I equals V. And this is like an equivalent resistance. We're saying that R1 and R2, if I add them together and just replace this circuit, like this circuit is going to have the same voltage and current behavior if I replaced it with a single resistor of value R1 plus R2. So if I have two series resistors, you can basically say that the resistances just sort of add. And the reason this worked out was that because they have the same current going through them. In the case of a parallel circuit, they have the same voltage across them. And so what you can do is you can say, like, I know that the voltage difference on the two ends are the same because they share the two ends. That's a real thing to identify about parallel resistances, is that the two nodes are shared for both resistors. They both see the same potential difference because they're both connected at both ends, right? And let's say this is R1 and R2. Now in this case, the voltage is the same. Like the V across R1 equals the voltage across R2 because that's the configuration for parallel. So if I wanted to compare it to an equivalent, circuit that had the same voltage, I would say, well, a V over R1 equals V over R2, and that equals V for the R equivalent. Then here's what V over R1 would be, is IR, so it's I1 times R1 equals I2 times R2, which equals I through this thing, we'll call it I equivalent, times R equivalent. All right, this is what we know. Like, the voltages have to be the same. Now, what we typically do in our analysis, we say, like, well, the I equivalent, the current through this circuit, should be the same as the total current going through these, because I'm replacing this with a single resistor. And so whatever comes in here has to split off into I1 and I2. Or in other words, the I equivalent has to equal I1 plus I2. The currents have to add because the current going through this thing has to be the same as the total current going through both those resistors. That's the idea of an equivalent resistance, right? And you can solve for the I1. The I1 is, like I said, like it's going to be V over I1 plus V over I2, V over R1. Because if you do V equals IR, how does the current of the resistor look like? It's V over R, right? So it's V over R1 plus V over R2. And similarly, the current, how is this guy found? It's the voltage over R equivalent. And the key thing is we're doing KCL. This is sort of like the current, the same current, but the voltages are the same across them. So you can divide out the V and you get this idea. And that's where the parallel series equation comes from. So these are the two resistance equivalences. If you see resistors in series or parallel, then you can collapse them. So let's take a look at this example. We have a circuit here. What is the equivalent resistance of the 30 ohm and 60 ohm resistor? Well, in this case, they're parallel because the two ends are connected to each other, right? So it's a 1 over R equivalent is going to be 1 over 30 plus 1 over 60. You can do your calculator for this. 1 over 30 plus 1 over 60, and I get 1 over 20. My calculator does fractions. And then you just flip it 1 over that, so the R equivalent is 20 ohms. So that means I can redraw my circuit as this. This is a 20, this is R, this is 20 volts. And we still have 0.8 amps going up this way. Okay? So how do we find the value of R? Well, I know the current. I can collapse these two into a single resistor. Because they're in series, it would be R plus 20. Okay? And now I know how much current is flowing, and I know the voltage, right? So I can use V equals IR, and the V is 20, 0.8, and the R is R plus 20, because these two are in series. Why are they in series? Because they have the same current going through them. Okay, so you can divide by 0.8. 20 divided by 0.8 gives me 25 is equal to R plus 20, so R has to equal 5 ohms. So that's like a little bit easier if you can collapse them than doing like Kirchhoff's current loop or voltage loop. We just sort of collapse all the resistors when we can. Which of the following combinations of 4 resistors would dissipate 24 watts when connected to a 12-volt battery? So that means we want 12 volts here. Oh, these are supposed to be 4 ohm resistors. Okay. So again, like if you're gonna do P is equal to IV, right? You could look at it from equivalent resistance. I know the voltage is 12, so for the I, I'm gonna replace it with V over R, right? Because V equals IR times V, which is V squared over R, is the power. And we want it to be 24 is equal to 12 squared over R. So you can find that the R that we want is 24 is 12 squared divided by 24, and I get 6. I want something that gives me a 6 ohm equivalent, basically, because 144 divided by 6 gives me 24. So this is 4 and 4. These are in series, so this gives me 8 ohms equivalent. Not going to work. This is 4, 4, and 4. When you do multiple in parallel, it actually extends. So you could say 1 over the R equivalent is going to be 1 over 4 plus 1 over 4 plus 1 over 4. Because even if you have 3 in parallel, it's the same idea. That's 3 over 4. And so the R equivalent is 4/3. Okay, so not this guy. How about, this one's a little tricky. This one is 4, 4, 4. All 3 are in series. This is going to be 12 ohm. I need 6 ohm as my target, so it's not this one. How about this one? This is going to be 4 and a 4 and a 4, but this is a 4 and an 8 in parallel, right? Because these two are in series, so you could say that that guy is the same as a 4 and an 8 in parallel. And I could do 1 over 4 plus 1 over 8 and do 1 over that to get the equivalent. And that's 2.67, so not this guy. Better be this guy. This is 4, this is 4, and 4. These two are in parallel. Why are they in parallel? Because they have the same voltage across them. So 1 over 4 plus 1 over 4 is 2 over 4, which is 1 over 2, and that's 1 over the R equivalent. The R equivalent for these two guys is 2. So this is then becomes a 4 and a 2 in series. And a 4 and a 2 in series is 6 ohms. You just add the 4 and the 2. So it's that guy right there. Okay. Example 3. When the switch is open, the circuit is shown above. The reading on the ammeter is 2 amps. So we have 2 amps while it's open. When the switch is closed, what's the reading on the ammeter? So what we don't know is the voltage, but we do know the 2 amps. How is the current flowing? Well, when this switch is open, the current can't flow through an open circuit, so it goes like this. This is the current, right? So these two have the same current, so you could say like, oh, well, from an equivalent resistance point of view, I know it's 2 amps going this way, and the equivalent resistance would be 35 ohms, and so now I know what the voltage is going to be, right? Because the voltage drop here is 2 times V equals IR. It's equal to 2 times 35, which is 70. So we know the battery is 70 volts. So here's the 70 volts. Now the question is, all right, how is it going to change now that when I close the switch, I don't know it's 2 amps anymore, right? So now it's going to be, well, what's the equivalent resistance, right? And then I know it's 70 volts because the same battery. All I'm doing is closing the switch. So I have to do, these two are now in parallel because they have the same voltage across them. They're connected. The 2 resistors on the top and the bottom are connected. So you do 1 over the R equivalent. So 1 over 20 plus 1 over 60. You get the R equivalent to be... My trick for this is I just add them and then I do 1 over whatever I get as a result. And so that's 15 ohms. So this whole thing is now 15 ohms. So you can replace it as a draw circuit like this. You can say it's 15 here from this guy. And then this whole circuit, this whole thing, I can replace with a 15 ohm resistor. Right? And then this is 70. And then these two now are in series. So now you can replace it with a 30 ohm. Just add the two resistances. And so what's the current? It's going to be the voltage across the resistor divided by the resistance. So that's 70 over 30. Or 70 divided by 30 is 2.3 amps. Okay?